Okay. Hello. Uh-oh. Did I turn it on? I think I did. Hello? Hello. Can you hear me? Yes? Louder? Louder? All right. Last class. Okay. Homework 6 due tonight. There's one more office hour today for demoing Lab 7. If you haven't already, most of you have, but you can't upload Lab 7 to Canvas. There's no assignment for it. So you do have to demo it in person, and if you miss today's office hour, we'll try to arrange one more office hour on Wednesday, and that will be the last possible opportunity. The write-up for Lab 6 is due tonight, and it will close. Good question. We should be able to find that out from Canvas, right? Somewhere. It was up at the top. Oh, okay. Yeah, this is different than my view. Okay. It will close on Wednesday. The write-up for Lab 7 isn't open yet. I will open it after class, and you will have till next Thursday for that one. And then the TAs will start grading, and they will no longer, those are absolute deadlines for those. Okay. And we have a final exam on Monday. It will be from 8 a.m. to 10:30 a.m. So you have 2.5 hours. It will be shorter than two times the midterms. So I think there's 13 problems. Okay. Maybe I'll add one more. So before no, no. Okay. Leave it at 13. Okay. Any questions? Yes. Yes. That's not it. Oh yeah. I don't remember anything like it. This one. What is this thing anyway? That's an inverter. Let's see. Where might we have seen that before? Possibly. Okay, so that would be 15. Okay, so if you put a multiplexer there, can you figure out what the output is? Well, so we know this is a multiplexer, right? That's an inverter. Kind of have another one here. Well, there are some problems that are meant to kind of stretch your brain a bit. This is one of them. So there's no step-by-step procedure to get to the answer, unlike the rest. I think I gave you a hint, didn't I? I mean, you can break this up and you can label these things. This is a multiplexer. Here's X, Y, Z. So you have a value now for this wire, or name it E or something, and then look at what you get from here. Well, once you get a Boolean expression, you could simplify it, right? It should be, once you simplify it, it should be obvious what it is. It's something you know. I won't say you like it, but it's something you know. Yes?
So I was wondering once we get the FPU and the FPV, I was wondering how exactly we're supposed to, is there a way to tell in the K-map where each variable goes? Or can it be random? When we draw the K-map, there's X, Y, or A, B, and C in this case, right?
Right.
And then how would we tell if A goes at the bottom, B's in the middle, and C's at the
Okay.
the left side of it?
So you can label it any way you want, but the problem is knowing what each cell corresponds to in terms of its minterm. Right? So that's helpful. Thank you. Have to switch. Okay, so there's a blank K-map. Okay, these two columns will correspond to variable, these two columns, and these two rows, and those two rows. So we have every possible combination of being in and out of the 4 variables. How would you like me to label the variables?
I just usually do A at the bottom, B in the middle, and C bottom.
Okay, so this is the way I taught you, or we did all the examples. This is for a function f, a, b, c, d, right? And if we do that, this cell is 0, 0, 0, corresponds to not being in any of the 4 variables. And this cell corresponds to being in all 4. Okay. Those are the only 2 cells that don't care how you label the K-map. You could label it any way you want, and this is still 4 zeros, and this is still 4 ones. But the others care. So for example, if we want the minterm corresponding to 0, 1, 1, 0, we need A to be 0, so we're in this half. We need B to be 1, so we're in B, so now we know in this column. And let's see, we need C to be 1, so we're in these 2 now. And we need D to be 0, so we are here. Okay. If I label it some other way, if I switch B and D or C and D or A and C, this cell might move. Okay. Now, we always do it a standard way so that we know that this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and that one's 15. And that's by using, in order, A, B, C, D. You can do it in some other order, but then these numbers move around. And then you have to figure out. Okay, so the suggestion is always label it this way, because then you know. Okay, but it is possible to do the problem correctly some other way. In fact, way back in the dark ages, when I took logic design, we did it this way. We did row major. Okay, and that's perfectly reasonable, but then this would be A and this would be B. Okay, I stick to this because this is what was used in the text, and it's confusing enough. All right. Okay. Other questions? There were a couple requests on ED, on Ed. That one's kind of small, huh? I should make it bigger, not smaller. Okay. Is it still focused? Want to do this one? Not really. Yes? No. Oh, what do you want to do, Hudson?
Can we do the last one?
The last one,
Sample final.
this is not on the sample final, but all right. How many people want to do this one? 2, 3. How many people don't want to do this one? Okay, the 3 who raised their hand will want to do this win. The rest of you I guess, are tired. All right, so what do we do first? Invert what? We can't just invert. If you invert your expression, you're taking the complement of it, right? You're definitely changing it. Yes, what should we do? On the middle or. So this is the top level, right, operation. And so if I want to distribute the complement, I need to break it up around this. So what happens? Nothing happens. Yes? Okay, so this becomes an and. Okay, and then over here, we have the same thing, but with one complement. And over here, I'll copy this down again. Okay, make sure you don't lose a complement when you do this. Okay, and then I have the original complement, this one, and now I have an extra one. And some of you might have done this problem differently, where you first tried to simplify this part, but it might be easier to first bring this complement down because they're going to cancel out. Right? So this makes your life a lot easier. Okay, so this part is just going to become x bar plus yz and x plus y bar z bar. Okay, what happens here? Okay, so this becomes an and so we have x bar, y bar on this side, and x bar, z bar on this side, and we complement them. Okay, I don't actually need to put a parentheses now because these are the same operations. Doesn't matter what order they happen to be. If you want to put the parentheses, go right ahead. Okay, what's next? Yes. Okay. So this is x plus y, and this is x plus z. And then I have x bar plus yz and x plus y bar z bar. Yes.
The left side turning to x plus yz.
Okay, so this is this strange factoring or distribution law that you can only do in Boolean algebra. Okay. What happens next? Yeah.
The x plus yz and the x bar plus yz, isn't that simplified to just yz?
Under what rule?
The same rule we just applied on the left side? The strange distributed law?
Well, okay, so you want to have x times x bar plus yz.
Yeah.
Okay, so now we have yz in common, right? And so we pull a yz out of both of these, leaving behind an x and an x bar, which are still anded. And then we have this guy. Okay, so this is 0, so it's going away. So we just have yz and x plus y bar, z bar. Okay, so let's just write this out. X, yz plus yz, y bar, z bar. That's 0. So we have x, y, z. Okay, so just be careful. Make sure you know how to apply De Morgan's law, right? Make sure you're breaking it up around the top level when you have a complement, and you have to swap the or and the and when you distribute the complement. That's De Morgan's law. Okay. All right. Don't want to do that. So I do have another one if we run out of things to do. I had a request to do one of these where we extract the transition table and the state diagram. Right? Does anybody want to do this? Yes, you want to do that. You want to do that. Okay. So we give it a circuit. Probably the best thing to do is first figure out what are the expressions for the inputs to the two flip-flops and the output. All right, so X is the input, and then of course we have the values held by the two flip-flops. And so we need to figure out D1. Okay, so what expression would I get for D1? Yes. Yeah. Okay, can I simplify this a bit? Okay, that's going to be make it easier for me to fill in the table. So I'm going to write X XOR Q1 bar plus Q naught bar. Okay, what about D0? Yes.
X and bar Q0 or X and Q1 or Q0 and Q1.
Okay. What about Z? Yes.
X XOR Q1 or not X and Q0.
Okay. All right, so now we have expressions, and we can now figure out the values for each possible state and input. Okay, so I have two state bits, and they have 4 possible values together. And I need to figure out what D1 and D0 will be for each state, and also for the 2 values possible for the input. Okay. Now is probably a good time to answer this question. Is this a Mealy or a Moore machine? Mealy, okay, because it depends on X. Okay, which means I need 2 columns here. That's the bad news. Because I need to consider the value of x here. Okay, so I can go in and do individually every single value. There are, let's see, we will have 16 in here and 8 in here. That's 24 different values to figure out. Or another way to look at it is, well, we've broken down each of these into things that almost look like sum of products. This isn't quite a product term, but I can easily figure out the XNOR. And so what I could do is just figure out in each column where the ones are, and then fill the rest with zeros. And that's a lot faster way to do it than to individually plug in 0 and 1 and repeatedly 24 times. Okay, so let's do that. So let's look at D1 first. So D1 is going to be the first column. And D1 is 1, well, when Q0 is 0, right? Because this is an OR. So whenever Q0 is 0, D1 is 1. So that happens, let's see, that happens here and here. And it also happens when X is 1, right? So I can put 1s there. Okay. So when Q0 is 1, then this doesn't help. So let's look at this term. So where is this 1? Okay, so this is an XNOR. So it's 1 when X and Q1 agree. Right? An XOR is 1 when they disagree. So an XNOR is 1 when they agree. Okay, so when X is 0, we want Q1 to be, it'll be 1 when Q1 is 0, so that happens here. And when X is 1, that happens here. Okay, and that means that that's it. Those are the 2 possibilities, so the 2 remaining spots get 0. Okay, D0 is a little simpler because we don't have that XOR to worry about. Okay, so where is D0 going to be 1? Well, when X is 0, these 2 terms go away. So the only way it's 1 is if both Q0 and Q1 are 1, and that happens here. Okay, so we can put zeros here. All right, now when X is 1, well, we have several possibilities. Again, Q0 and Q1 could both be 1. And then if Q1 is 1, we're also 1. And then if Q0 is 0, we're also good. So that's 0. And then we fill the last spot with 0. Okay, so there are different ways to fill in the table. But you'll go much faster if you use a strategy like breaking it into a sum of products and filling in where each product term is 1. Okay, let's do Z. Okay, so where is Z going to be 1? Well, when X is 0, that happens when Q1 is 1. So that's here and here. And then when X is 1, this doesn't help at all. Okay, this term is when X and Q1 disagree. Okay, since X is 0 here, that happens here. And when X is 1, that would mean Q1 would have to be 0, and that happens here. Okay, so we filled in our transition table. Okay, you can use whatever technique you want to fill this in based on the equations. But I highly recommend not doing them one by one. Okay, all right, so from this, we can then make an encoded state table. I'm going to use the boring symbols, A, B, C, D, and our table becomes A, B, C, D. This is the present state. The next state then depends on X, whether X is 0 or 1. I can recopy the output, but that's not really important. Okay, so what state is this one? C. So this is C, C. Oh, lots of C's here. B. B? D. Oh, okay. D, A, D, D. Okay, so all we're doing is we're using our encoding here, replacing it with the letter. Okay, so from here now we need to draw the state diagram. Looks like a lot of traffic going to C. So here we'll draw A. So A with a 0 goes to C. I'll put B down here. B with a oh. There. You still see the table, okay. B with a 0 goes to C. C with a 0 goes to C. D is the only one that goes to something else with a 0. Okay. A with a 1 will go to D. B with the 1 will go to A. C with the 1 will go to D. And D will go to itself with a 1. Okay. Are we done? No. Okay, what's wrong? Okay. So now I have to go put the outputs on the arc. Okay, so when we are in A and we have 0, that's 0, but with a 1, that's a 1. For B, it's 1 in both cases. For C, it's 1 for 0, and I wrote D instead of 1. Okay, and for D, we go to output a 1 and a 0. Okay, so this is all mechanical. And when this is analysis, taking a circuit and obtaining its state diagram. And synthesis is the reverse process. Given a state diagram, produce the circuit. Yeah?
So with a Moore machine, the outputs would be with the A, B, C, and D and not on the arcs, correct?
Well, all right, so that's kind of tricky. If they are in the states, then definitely it's some more. But let me ask you this question. Is this a Mealy or a Moore machine? How many people think it's Mealy? Okay, how many people think it's Moore? Okay, so even though I wrote the output on the arc, you'll notice that when you're in A, we're outputting in 0 both times. So our output, I could have just written it here. Okay. Likewise, if we're in B, we're always outputting a 1, so I could have written it there. Okay. So just because it's on the arc doesn't mean that it's necessarily Mealy, but that's kind of mean to put it on the arcs when you could have put it in the state. Okay?
So if we're given an image like the flip-flop and we're told to make the state diagram, either of those is correct?
Yeah.
Okay.
In fact, I think on the midterm too, a lot of people wrote the outputs on the arcs, even though it was a Moore machine, but they wrote them correctly, so that was fine. Okay, you understand the difference is that in a particular state, do you need to know the input to know what to output? And the answer is no. You can output 0 either way. Okay. All right, so those were the 2 requests I had. So now I have a bunch of other things that have been requested in the past, or I could take additional requests, or we could go study. Yes.
Could you do an example of making a CMOS gate from a Boolean expression?
Okay. You have a favorite? Oh no, you're going to give me the homework one, right? All right, I will make one up. How about A bar, B bar plus C bar. Can I invert all the inputs?
Sure.
Okay, thank you. Maybe I should make it smaller. Can you still read that? Okay, you want another variable? All right, how about A bar plus D bar? I think that's simplified, but anyway, okay. All right, so this is the function of A, B, C, and D that we want to implement. So whenever this expression is 1, we want to pull up the output. We want the output to be 1. So we need to make a network that connects the output to the power supply when this expression is supposed to be 1. Okay. And we have to build it out of PMOS. And remember, the PMOS transistors conduct when their gate input is low. Okay. So, so here's my power. How shall I construct my PMOS network? Yes? A naught and what? Okay. Okay, so the first thing you wanted to do is this, right? Now, do I need to put a naught here? No. All right, because I want this to be, when this is 1, the A bar will be 1 when A is 0. So this is perfect, right? When A is 0, this will conduct. Okay, so if somebody's nice to you, they will give you an expression where all the literals are complemented, so you can just use them directly on the PMOS gates. If you have something, if they throw in plus G, you'll need to invert G. Okay. Let me take that away. I don't want to do that. All right, it's gone. Okay, so what was the other branch? Okay, so now we have a branch which requires C to be 0. And then we have a choice, either A or D. Okay? So you can see that whenever we have an AND, we had a series connection. Here we have an AND here, so we have a series connection, but the second part is actually a parallel connection. Okay. All right, so that's half the problem. So F will be 1, or it will be pulled up when F is supposed to be 1. But now we need to make sure that it's now grounded, or when F is supposed to be 0. So we have to get the pull down function. How would you like to do that? What? Not everything. Okay, so we'll take It's
De Morgan fit all the way down.
De Morgan. All right, so we get A bar, B bar, bar. This OR becomes an and then over here we have C bar, A bar plus D bar, bar. Okay, and this one is going to become A plus B. Note I need to add those parentheses. Okay, because I want these two to be combined before the and. Right? If without these parentheses, this becomes A plus B, and B is ANDed with the rest, not the whole thing. Okay, so when you do this, sometimes you need to add those parentheses. Okay, let's see. This is another case where I'm going to need to add those parentheses. Okay, so we have A plus B, and then this is C plus AD. Okay, so this is when we want to make a connection. This expression is 1 when we want our function to be 0. Okay, I'll help you. I'll draw the ground symbol. You want to simplify it? We could, or we could just do this directly. Right? We have an and, so we'd make two networks and connect them in series. So what would this one look like?
A and B side by side.
Right, okay, so A and B. Okay.
On those same lines, C will be on the left, and A and B will be on the right.
Okay, I have C over here, and then I have the other option is both A and D. Okay. Okay, so this will connect to ground only when this evaluates to 1, meaning that either A or B or both have to be 1, and then either C or both A and D have to be 1. Okay? Yes?
And then they're made of different materials.
Okay, so this is the symbol for a PMOS transistor. Okay? This is the symbol for an NMOS. You cannot move this bubble. It's part of the symbol. Okay? If we take this away, then it becomes an NMOS transistor, and you can't use NMOS to pull up. It's not good at it. Okay, so these are different types of transistors. Not only are they on for different voltage levels, but they are just different, they are constructed differently. Okay. All right, anything else people want to see? Long quarter. Yes?
Can you just briefly show how to not one of the symbols?
Not one of the symbols.
A bar.
I get one of the ones on the top or
You want me to put that plus G back? Okay, so now we have a third option is, well, G could be 1, right? So we now have 3 ways that we could connect F to the power, so we now need G. Okay, so I'm going to put another branch here with another PMOS transistor. Okay, I have to use PMOS transistor. In order for this to be on when G is 1, I'm going to need to connect G bar to it. Okay, but G bar is not one of my inputs. Likewise, if I want to ground this, I've got to make sure that, okay. All right, so when we complemented this, we had a plus G, right? So if we were applied De Morgan's law, then this would have been like that, right? And a G, okay. And so this would have been and G bar, and we've still had an and G bar. So it's a good thing I left myself room here. You may bring white out to the final exam, but I don't recommend it. I have on occasion seen somebody work out a problem completely correctly, drawn an X over it, and done something else. And because they didn't have whiteout, I could see what they had done, and they still got a lot of credit. Not all of it, but a lot of credit for actually having worked it out correctly the first time. So there will be extra paper. You do not need to cross out or erase anything. Okay, all right. So I need to run this through a G bar here. Okay, so we will put an NMOS. Okay, now the problem is I don't have a G bar, so I'm going to have to create one. So, so how do I create G bar? I wish I hadn't written this here. Okay, so we have power here. So an inverter, right? An inverter is just a PMOS and an NMOS. Right, and that would be G bar. So what I do here is I would make a PMOS transistor, and then I wind it down here. Oh, okay, I shouldn't have drawn this. Okay, and this is my NMOS, which I will connect to ground. Okay, and so now this is G, and this is G, and then here I have G bar. So I can connect that one to there, and let's see. We'll have to grab this one and connect it to there. Okay, that's a little messy, but okay. That work? Yes? Okay. So basically you just add the inverter and then connect the output of the gate to where it needs to go. Okay. Hopefully no one will give you uncomplemented variable. Any questions? Any other questions? No other questions. Let's see. So, what are the options? No. Yeah. A transmission gate. So a transmission gate, right, is a PMOS and an NMOS in parallel. Right, and we usually draw this symbol to represent that. And we often use the same control for both of these. They're either both on or both off. but since one of them is on when its input is low and the opposite for the NMOS, we usually add an inverter, right? So we do something like that. Okay, so let's say this is A, and we'll call this one B. Okay, so we can make a little truth table. We'll call this one C. Okay, when A is 0, let's see, when A is 0, we have a 1 on this PMOS transistor and a 0 on this NMOS transistor. So what is C? Okay, it's high impedance. It's not, we don't have a value for C. Okay, how about when A is 1? When A is 1, now this PMOS transistor is on and this NMOS transistor is on. So C is, it's whatever B is. Or we could write it this way. If we want a full truth table, you could say, okay, 0, 0, 0, 1, 1, 1, 0, 1, and C is Z in these two cases, and in these two cases, it's whatever B is. Now, we don't have a logic expression for this. Z is not one of the Boolean values, right? So this is where you look at your circuit and figure out, well, when A is 0, is C connected to something else? Okay, and then when we did a multiplexer, right, we had a selector here, and we had input 0 here, and input 1 here, and the way this worked is, I'm not drawing this well. Right, we implemented this with 2 transmission gates, and when one of them was always conducting. Right, we did something like this, I think. And then we wired these two together. This is I0, and this is I1. Whoops, and this was S. So when S is 0, let's see. I think I got it backwards. When S is 0, then we have a 1 here, and we have a 0 here, so this one is sending out I0. Okay. And when S is 1, we have the opposite. We have I1. So even though the outputs here are not being driven, their value is provided by the other one. Right? You can't when you wrote your Vivado, your Verilog code in Vivado, you were not allowed to tie 2 outputs together. What happened when you did that? Yes. Yeah, you got the multiple driven net, right? You don't want to do that in an FPGA because then you're trying to drive an output both high and low, and you have basically a short. But in this case, we promise never to turn more than one of these on at a time. And in fact, one of them will be on it all the time, one or the other, because one of them is controlled by S and one of them is controlled by S bar. Okay, so that's kind of a lower level than the logic, right? That's below the level of the not and an OR gate that we started with. And there are things you can do at the level below that you can't do if we confine ourselves to just the Boolean operators. Yeah.
Can you make nodes wherever the wires are connected?
Sorry. Right, these two cross each other, but they're not connected. And this would then be the output. Right, S is so basically we have S bar controlling this one and S controlling this one. Yes. Okay. You want to do that? You want sum of minterms. You want a NAND. Okay, you want to pick some minterms? Okay. So we can write these minterms out directly, right? 0 would be A bar, B bar, C bar. 2 would be A bar, B, C bar. 5 would be A bar, oops, no, it wouldn't. A, B bar, C, and 7 is ABC. Okay, so a NAND is formed directly from a sum of products, right? Because all we need to do is, if we were to write an expression for this, we would just do A bar. And you can either put the bubbles here, or you can write A bar, B, C bar, okay? And I'm doing it both ways, so you know that either way is fine. Okay, so A, B bar, C, and A, B, C. Okay, now if we were doing a standard sum of products, I would just put an OR gate, one OR gate, to combine these, right, to do the OR of all product terms. But we can go directly NAND by NANDing these, right? And then I would have ended up with this gate by complementing each of these AND terms once. But this, fortunately, turns into a NAND. So all I have to do is feed them in here. Okay, the other thing, of course, you could have done, and you would have saved a little bit of ink maybe, is to pull out your old K-map. Let's see, 0. What am I doing? This is minterm 0, so we put a 1, 2, 5, and 7. And we come up with the expression AC plus A bar, C bar. Right? And so in this case, you could have a slightly smaller network. Oops. Yeah. Right. Okay, so what would my product of sums be here? It's easy to get confused here, right? Okay, so let's do this again. All right, I want a product of sums, right? So I would now circle the zeros and get product terms for the zeros. So I would get A bar C and A C bar, right? And so F prime then is A bar C plus A C bar, which means F is A plus C bar and A bar plus C. Okay, and so we do the same thing. We'd have our ORs. We'd have A and C bar, and A bar and C, and instead of putting an AND, instead of ANDing those, you would then use a NOR gate. Okay, it's really easy to get confused here. Don't hurry. Okay. All right, we have 4 minutes. Yes?
Really quick, could you explain the condition for a logic family, for why it would not be?
Okay. So basically there are two things that we have calculated about logic families. One, the noise margin, and two, the fan out. So if you have a negative noise margin, not only does it mean you don't have any room for noise, but there's a possibility that you could be sending a signal that's not interpreted the way you want. Right? So it means that your output high region might actually be lower than what's considered a high on the input. Right? You want them the other way. Or it could be at the other side, on the low side. It could be an output low might be higher than what's considered a low on an input. Okay, so that's one reason why that would be a problem to use this logic. The other problem is if your output doesn't supply enough current for one input, that's bad. So look at how much current an output can supply, both when it's trying to drive and trying to sync the loads, and see how many inputs it can handle. Hopefully it can handle quite a few, like 10 or 3 or 4. Even handling only one is a problem because generally you need your logic to fan out. But if it can't even handle one, that's impossible. Okay, so of course this is totally not realistic, this question. It's asking if you understand what noise margin and fan out are. Okay. I think once I had a problem where there were 4 different parts and you were asked, you had to meet a certain fan out and a certain noise margin, and you were asked which was the cheapest one that met your requirements. Nobody liked that question. Okay. Any other questions? No. Okay, then I'll see you on Monday.